Okay, so yeah, hello everyone. Welcome to the final session for the tutorials on design analysis of algorithms. And so what we'll do today is a quick review of whatever we saw throughout the course, and we may not be able to. So we'll do this through problems because I mean that's the best way I think to do it. So we may not be able to cover each and every topic that was covered in the entire course, but the major ones um, we'll try to do as much as possible. So there's some question in the group. So okay, so the content in the course lectures. Okay, so in the exam, I don't know what kind of, I don't know if it's going to be just MCQ or if there will be descriptive questions. But yeah, like I said in the last time, you can use the portal, the group discussion portal on Google Groups, because this is completely out of my domain. So the people who are so these are, I mean, different people doing different jobs. So I think if you write your query on that group, I think yeah, maybe you'll have an answer to your questions. And regarding the tutorials, the yeah, so I mean, I'm just trying to yeah, I mean, I'm just trying to explain the concepts through examples. So which will just help you to solve the assignments, because of course both are at different levels. The questions in assignments would be slightly easier than what we cover in the tutorials, but I'm just yeah, so I don't know though what the questions will look like and what the difficulty will be. So is that fine? So you can just use the Google groups on the SWAYAM portal. I mean, the discussion forum on the SWAYAM portal. Okay. So yeah, if you're speaking, I don't know. The mic is on, but I can't hear you. Okay. So yeah, are there any other questions before we get started? Okay. So if not, let's get started. So um, I'll just um, yeah, I'll just try to cover um, as many topics as possible, but we'll do it through examples. Okay. So okay. So let's start with um, yeah. So let's start with the Tower of Hanoi problem. I don't know if you have already seen it, but it's a nice example to recall the concepts. So it's the Tower of Hanoi um, problem, and what it says is that you have three pillars. You have three pillars like this, and you can put insert discs in it. So there are different discs. There are n many discs, and they're all of different sizes, all of distinct sizes. So let me say 1, 2, 3, 4, 5, and they're in the sorted order. Now, what you want to do is yes.
In the point of view you telling like what we know like that no ma'am. In that you in tutorials some of the problems we explain you explain ma'am. In that there is no options at all like a quiz type. In that type of questions may be asked in exam. What we can do ma'am, we can all I mean you solved where it is like that we want to solve or how we can write ma'am.
Okay, so yeah. So if there are descriptive type questions, then yeah, if they're asking you specifically to design the algorithm, then um, I don't know, I can't hear you if Sai Pritam, if you are speaking. But yeah, to answer the question, yeah, so if say there are questions of the following kind, that you design an algorithm for a specific problem, then you can write a pseudocode. Unless they're asking you to code, that I don't think will happen, but I don't know. But then you can write the kind of algorithms that we saw in the tutorials. And um, yeah, so majorly if there are descriptive type questions, then you'll do as we did in the tutorials. And yeah,
It is also in online, no, ma'am. Like that. In that case, I am asking.
it's also online in the sense I didn't understand.
Online in the sense what you explained, that particular algorithm, that is we want to write down.
So are you saying, if such a question gets asked, you would uh, sorry, can you ask again? I think I didn't understand properly.
In online mode means, you tell me, no, ma'am, within the pen. I mean, pen that we want to type as an answer in the exam session.
Okay, so okay, I just want to clarify one thing. So is it an exam on paper or is it an exam on computer?
Computer, ma'am.
Oh,
Online.
oh, okay. And what is the duration of the exam?
2.5 hours, ma'am, mostly. 2.5 to 3 hours, they are telling.
3 hours.
Okay, so okay, so if it's a typing exam, then yeah, then I'm not sure if they'll ask algorithms and so on. But yeah, if they do, then yes, you'll have to type it. Mm, okay, but I think you were asking for this last time, no? Whether there are MCQs or descriptive. So did you post it
Yes.
already on the forum?
They're having a descriptive and quiz type, ma'am.
Ah, okay,
Both is
okay. Oh, okay. So okay, thanks for yeah letting us know. So then yeah, then you will have to type it. Yeah.
okay, ma'am. Thank you, ma'am.
Okay. Yeah. So that means you may not be able to draw diagrams and so on if you need to, but maybe they won't ask you questions like that. Okay.
That's why I'm also asking, ma'am. Why
Mm,
means, we want to draw the diagrams and we want to
mm,
explain moreover. That's why I'm
yeah.
asking. So this problem session record sheet also available, ma'am.
Yeah, we'll record and upload it.
Okay, ma'am. Thank you.
Okay, good. So yeah, we'll start with simple example that you might have already seen. Okay, so okay, Sai Pritam, if you can hear me and if you are not speaking, can you please unmute? Can you please mute? Um, okay, so yeah, okay, thank you. So yeah, so let's recall the problem. So you have some disks that are piled up in increasing order. All of them are distinct, and what you want to do is you want to transfer this whole thing. So I'll call this ABC. You want to transfer this whole thing to C. Okay, and this is what we want at the end. This is what we want to achieve. But the problem is that I can't just lift everything from the bottom and transfer it there. I have some limitations. So what are the constraints? The constraint is that you can only pick one at a time. So you can only oh, sorry. I'm really sorry. So the constraint is that you can't put a disk of large length on top of the small length. So you're not allowed to place a disk of large size on top of a disk of um, small size. So at any point of time, you can only you have to maintain it in the sorted order. So what is the algorithm for this? If you remember, please please tell me. That will help us speed up. Or have you not seen this? I'm not sure.
Using Tower of Hanoi.
um Sorry, I couldn't hear you. Yeah, can you please? Okay, so
Using the concept of Tower of Hanoi, destination, source, and abstract.
okay. Okay, so, and yeah, someone says recursion. So yeah, so we'll just quickly.
Not recursion. So Tower of Hanoi, using source, destination, and abstract attribute. Three steps we have to get into the steps. Tower of Hanoi, n minus one, source, and destination.
Yeah,
The
so the
form.
okay, but the algorithm that you end up writing. You can write it iteratively, you can write it recursively. So you can think of these as smaller subproblems. So you can also do it using recursion, but the idea you're saying is fine, I think. So um, you're saying that at any point of time we're going to do three steps. One is that um, yeah, so one is that I definitely want this disk 5 to come here at C. So the only way that I can do that is I'll have to somehow bring this four disks. I'll use the B as a temporary place, and what I'll do is I'll somehow get the four disks on top of each other, and then in the next step, so this will take some x many steps, k steps to achieve this. Then what we will do is we'll simply take this disk of largest size, and we will and we will keep it here. So then what you need to do is you again need to get these four disks and uh, get those from B to C. So you have A, B, C and ABC. So we divided this task into three steps. One is that first, get the n minus 1 disks from A to B, and then you take the nth disk from A to C, and then the remaining n minus 1 disks from B to C. So yeah, so that means we divide. So then what we do is, in order to solve this problem, in order to solve this subproblem, what we'll do is you'll again use the same idea. So in order to get this here, first you will have to get 4 here. To get 4 here, you will have to take the remaining 3, put it in the temporary, and get 4, and keep on doing this. So I mean, it's the same idea that you're applying again and again, only that the size of the subproblem reduces, and you have to use the empty peg as your temporary. So that may be A, B, C, depending on where you are, where you want to put the next disks. But yeah, I hope everybody remembers this. If that is clear, can you tell me the recurrence relation? So if T of n is the number of steps needed to solve the Tower of Hanoi on n disks, okay. So yeah, I think there's one answer. There's one answer in the chat which is correct. So the answer is that to solve the problem on n disks, what I'm doing is I'm first solving the problem on n minus 1 disks here, which is by taking everything on the top and pushing it on the other pick. So what I'm doing is I'm spending t of n minus 1 time for that. Then once the disk that I wanted to move to the correct position is free, we're going to take one step and push it there. So that will take, let's say, order 1 time, and Finally, we are solving the same problem again, but from different place to different place. Now I want to move from B to C. So this is again a subproblem of size n minus 1. So finally you get 2 times t of n minus 1 plus 1. And how do we solve this recurrence? So what are the methods that you know to solve the recurrence relations? So one method that you know is the substitution method. So substitution method is very simple. It may not work all the time, but in this case it does. So this is solving recurrence. Yeah, you can use Master's theorem also. That was something that we did not do in the course material, but yeah, sure, you can use that. So yeah, so then how do we write this? This is same as 2 times t of n minus 2 plus 1 plus 1. So this will be 2 square t of n minus 2 plus 2 plus 1. And if you expand this further, this will be so I can just write 2 as 2 to the 1 and 1 as 2 to the 0. So finally what happens after k steps is, what do we get after k steps? Okay, so after k steps you'll have here 2 to the k times t of n minus k plus 2 to the k minus 1. If you keep expanding, you can see this pattern, and 2 to the k minus 2 and so on up to 2 plus 1. Okay, and when does this problem become trivial? So after how many steps will this become constant sized? Let's say size 1. Okay, so if you take k to be n minus 1, so after n minus 1 steps, what will happen is t of n is 2 to the n minus 1 plus, times t of 1 plus 2 to the n minus 2 and so on up to 2 plus 1. And what is the value of t of 1? T of 1 just means that you have this peg where there's only one disk, and I just want to get it from A to C, so I can simply do it in one step. Simply take the disk and keep it on C. So this just take one unit of time. So this will be 2 to the n minus 1 plus 2 to the n minus 2, so on up to 1. And this is nothing but your geometric series. And yeah, so you can if you solve this, you get this answer. So okay, so yeah, so can someone tell me whether the answer that we said that e of n is 2 to the n minus 1? So okay, so can someone tell me whether this is an upper bound or a lower bound? So for solving the Taro-Fenoy problem, should I say that the running time of this problem is always order 2 to the n minus 1, or is it omega 2 to the n minus 1? Is the meaning clear? So this is an upper bound and this is a lower bound for this. So if you read it, this would mean that to solve the Taro-Fenoy problem, you need at most some constant c times 2 to the n. So I'll just skip the 2 to the n part, I mean the minus 1 part. So is it this, or what did we prove just now? Did we prove the order part, or did we prove the omega part? Any guess is also okay, or if the question is not clear, then yeah, please ask. Okay, so yeah, okay, maybe let me just answer that. If there are questions, then let me know. So so what we're saying is that you want to solve this problem, and there could be many ways to do that. So that there could be different algorithms. The one that we saw is just one approach of doing it. So if you're saying that, okay, look, here is an algorithm to solve tower of Hanoi problem which takes this much amount of time, then you're just saying that the optimal solution for tower of Hanoi will run in time at most order 2 to the n. Because why are we saying at most? Because you have one algorithm which takes this much time, but there could be some other algorithm which can do better. So you are just demonstrating one way of doing it, which is this particular algorithm that we said, solving for sub problems, combining them to find the solution to the whole problem. So yeah, so therefore what you are showing is actually an upper bound. You're just saying that it's at most 2 to the n time, because you already have demonstrated one algorithm. But if you want to say that you can't do better, that means claiming that it's lower bound, it is a lower bound, would mean that there cannot exist an algorithm which does better than this. So so yeah, so what do you think, is this true? So first of all, does everybody agree that it's at most um, does everybody agree that it's order 2 to the n and at the moment not omega? Is that part clear? Okay, so so yeah, I yeah, so are you so do you think it's also tight in the sense that there does not exist an algorithm which can do better than 2 to the n minus 1? So how many think you can do better? Okay, does anyone think you that this is the best time that you can get? Okay. Okay, so let's see. So the answer in this case is actually yes. It is actually it's the best that you can do, but that's not the case every time. So for example, you have seen algorithms for the minimum spanning tree and Kruskal's and so on, and when you demonstrate one algorithm, it takes some amount of time. You are not saying that you can't do better than that. You are just demonstrating one such algorithm. Hence, you are always giving an upper bound. Whenever you give an algorithm and you analyze the running time, it's always an upper bound. If you have to show lower bound, then there are it's difficult to prove that something is, I mean, is omega of something. So in this case, we can show that with not, which is not very difficult. So we'll try to maybe you can try to come up with an argument right now. So why do you think you cannot do better than this 2 to the n exponential time? Any thoughts? I hope the question is clear. So what I'm asking is that if you want to show that there is an order 2 to the n time algorithm, then here is one algorithm which you have already demonstrated. That part is fine. But if you want to say that it's a lower bound, you want to show a lower bound of 2 to the n minus 1, then how will you prove that? for this particular question only. So you want to say that you cannot do better than this time. Okay, so I'll just give you a proof sketch which looks very similar to very similar to the argument we saw, but it doesn't always work for every algorithm. So in this case it does. So the proof sketch is that if I want to solve this problem, then I'm going to have to first take the largest size disk and place it here. That is the first thing I want to do, because placing 4 or 3 or anything else there is not going to help me. I'm going to have to bring this anyway. So in order to do that, I'll have to move the whole block above it somewhere else, so that this becomes free and I can freely keep it here. So we're saying that in order to find the minimum number of minimum number of steps needed to push nth disk to its destination, which could be, in this case it's C, but it depends. So is that you first solve it for the remaining n-1 optimally. So this you solve optimally, and then the next optimal step is you push the largest size disk to the push the largest disk to its correct position, and next thing you do is you again have to bring back the whole thing on top of the largest disk. So then you have to solve the n-1 part optimally. So so then if you do the analysis, you'll end up getting the same number, but only with this inequality. You'll end up showing that p of n is at least 2 times p of n-1 plus 1. You solve it, you get the same thing. The only thing that was different here was the fact that in order to take the first step, you have to solve this part optimally with minimum steps, you have to solve this part optimally with minimum steps, and finally this part. So this is something that is obvious in this example, but as you can see, if you take any other algorithm that you have seen, say shortest path or anything, arguing this optimally is not easy at all. And yeah, so if this does not make sense, then don't worry about it. It's just a philosophical sort of argument. But yeah, if it does not make sense, then don't worry about it too much. So the only takeaway, I just want to I just want to quickly recall the idea of recursion that you saw and how to form the recurrence relation. And one way of solving it is through substitution method. And yeah, like some of you pointed out, you can use different methods such as Master's theorem and so on. So yeah, if that is clear, yeah, what we'll do is maybe I'll try to get some greedy. Yeah, so so you saw some sorting algorithms, and yeah, so so which one of them are maybe I'll so there are different algorithms you saw. So you saw this bubble sort, you saw quick sort, there was merge sort, and then you had selection sort and insertion sort. And you saw that these algorithms take order and square time. This is something we'll not get into, and these take order and log n time. So the analysis of the merge sort was deterministic. It's a deterministic algorithm, but for quick sort you use the randomized analysis for it. And there's one more sorting algorithm that you saw, which was heap sort. and this also runs in order and login time. Okay, and one thing that you might have noticed here is that these kinds of problems have a different flavor, in the sense that given an input, there is one fixed output that is there. So it's just one-on-one sort of a relation. But so there's no optimization that is happening. There is a problem given to you and there's a fixed answer that is correct. I mean, that's what you are expected to output. But there are also problems where you want to maximize something or you want to minimize something. So for example, you can think of the shortest path problem. And um, yeah, so here you had some source and some target given to you in the graph, and you were supposed, there are costs on the edges, so we saw this weighted version of graphs. And there could be multiple paths from S to T, and you want to find the one which is the shortest, in the sense that if you sum up the costs, it should be the minimum. So there's some kind of an optimization here. So either you are interested in finding minimum cost or maximum of some quantity. So these kinds of problems are what are called optimization problems. And there are two techniques that you saw for solving such problems. One is the greedy, and the other is the dynamic programming. So both of them typically give you polynomial time algorithms, not necessarily always, but but both of them are nice strategies which do not work all the time. So it's not necessary that for every problem you have a greedy or you have a dynamic programming solution, but there are several certain problems for which these are suitable. So what we'll do now is we'll just quickly maybe take few examples of greedy. We'll do some examples of dynamic programming. So okay, so let me just start with a simple example. So the question is that you have a car, and let's say you want to travel you want to travel some distance. So there's this there are several cities that you want to visit. Along the way there are several petrol pumps. So this is the petrol pump P1. There's some petrol pump, so sorry, I'll just, yeah, so there's a petrol pump P1, there's a petrol pump P2, and so on. There's a petrol pump PK. So there are and in between, so basically the towns may switch somewhere in between. So it's not necessary that in every town there's a petrol pump. So we'll not worry about that, but you just know where they are located. So maybe this is at a distance of 3 kilometers from the beginning. This is maybe at a distance of 10 kilometers from the beginning, and so on. So you know how far they are. And the problem is that your car cannot hold an infinite amount of petrol. So you have a limit, you have some limit on it. So if you fill it, let's say you filled your I mean the full capacity of your tank in the tank, then you can travel, let's say 10 kilometers. So if you assume that this car is capable of traveling maximum of say 10 kilometers. Okay, so so then notice that if you if you, let's say you keep traveling at some point, and let's say then you decided you would have exhausted some petrol, then at some point you decide to fill it. Okay, and then you move some distance. Okay, and you keep on doing like this. So the question is, one thing that you can do is maybe, okay, at every point, so let's say I travel some distance, I reach the first petrol pump, I'm going to refill my tank. Then I travel how much distance I can before I reach P2. Then in the second petrol pump also, let's say you decide to fill it again, and you do it every time you come across a petrol pump, maybe you fill it. Okay, so then you'll definitely reach the destination. But yeah, then you'll definitely reach the destination. But what I want to do is I want to minimize the number of petrol pumps that I visit throughout my journey. So this is exactly what I was saying earlier. So there's a contrast between the sorts of algorithms you saw earlier, I mean in the first part of the course, and what you saw in the second part of the course, where there's always some kind of optimization. There's something you would like to minimize or maximize. That's the kind of nature these problems are. So whenever you see some quantity being minimized, maximized, uh, typically you can try using the greedy or DP algorithms. So in this case, I want to minimize the total number of petrol pumps that are visited before. Yeah, I mean, yeah. So then what would you do? Any you can think of any algorithm, but right now if you come up with a greedy strategy, that would be nice. So yeah, if you have any thoughts or ideas, I'll wait for a couple of minutes. You can, yeah, you can share with me. They need not be correct. um, any idea is welcome. So any thoughts? Okay, I'll just wait for some more time, then we'll start with the answer.
At each and
Yeah, Ishwar Krishna. um,
yeah, ma'am. Actually, what I was telling is, at each and every petrol pump, we can fill the maximum petrol that a car can hold. Maybe this approach can give the best result.
um, okay, okay, okay. Yeah, so I'll get back to you. So yeah, so regarding the comment that you have in the chat, so yeah, I myself don't have any um, yeah, any way of providing feedback, but as a student you have this Google form that's provided to you, right? So you get a Google form each week after the content of every week is released. So yeah, so um, you can give your feedback there, and they'll definitely take a look into it. Okay. Okay, so yeah, getting back to your approach. Okay, so what we'll do is, yeah. So you're saying that, let's say if you assume that the tank is full, you can cover a distance of 10 kilometers. So what you'll do is you'll go as far as possible within the 10 kilometers. So let's say within the first 10 kilometers, the final petrol pump, the last petrol pump that occurs is at P2. So at this point you'll refill your tank. Then let's say the next petrol pump occurs only at 17 kilometers. So that means if you look at the next 10 kilometers, maybe there are some in between, but within the next 20 kilometers, this is the last petrol pump that you have. So then you'll go as far as possible from there. At this point, if you don't fill it, okay, you can only go 3 kilometers further, but there's no petrol pump at 20, so you won't be able to move further. So you're forced to refill your petrol at 17 kilometers. Similarly, if you keep moving ahead, okay, then you look at the next okay, so maybe I'll just draw this again. So I'll just start with an example. So let's say you have at 3, you have at 7, you have at 10, then you have at 17, 12, okay, and then maybe let's say 30, 38. Okay, so this is the example. So when I write this 3, 8 and so on, what I'm saying is there are petrol pumps at those distances. So like you said, we are starting here, and the maximum distance I can go before my petrol is exhausted, which is 10 kilometers. I can walk 10 kilometers. At this point I will refill my petrol, okay, and from here I again have a capacity of going 10 kilometers further. So I look at 10 kilometers further and I find the final petrol pump here. I'll fill it again, okay, but now you're not going to look from 20 to 30. Why is that? Because right now you are at 17. From here you can only go 10 kilometers ahead. So from 17 you're going to look 10 kilometers ahead, that is up to 27. The last petrol pump that occurs before that is 23. You'll fill it again at this point. From 23 you're going to again look at 10 kilometers ahead. So where do you fill next? Okay, so is this making sense to everyone? Okay, so if it is making sense, then please answer. Even though it's simple, please answer. Otherwise, I wouldn't be sure whether, yeah, I mean, whether you've been convinced or not. Okay, so then I look 10 kilometers ahead, which is up to distance of 33, and the last petrol pump that I see is at 32. So I fill it again there, and finally I look 10 kilometers ahead, which is up to 42, and at this point I can even reach 42 without even having to fill the petrol at 38. So how many times did we fill the tank? One was at 10, the other was at 17, then we had to yeah, then at 23, finally at 32. So there are 4 points only throughout this journey of 42 kilometers where we ended up filling the petrol. So I'll just write the algorithm and then you can try to come up with an explanation for. So there are two things. Whenever you write an algorithm, first thing is it should be correct. Second is you should analyze the running time. These are the two things. So I'll just write the algorithm. The algorithm is that, say you are right now standing at point x or distance x, then you look 10 kilometers ahead, so x plus 10, and find the last petrol pump ahead within that distance. and you're going to fill it there. So let's say that happened at y. So let's say this happened at y. Then you're going to look from y to y plus 10 and repeat the same process. So basically you're looking 10 kilometers ahead, finding the last one and filling it and keeping on moving ahead. So this is the algorithm. And how much time does this take? So the input to you can think of the input to you as an array where you've been given these distances 3, 8, 10 and so on. So what is the running time of this algorithm? Is the algorithm clear? Yeah, please. Sorry. Is the algorithm clear? If not, please let me know. I can explain it again. Okay, thank you for yeah. So if that is clear, can you tell me what is the running time of the algorithm? Uh, I mean, any guess is okay. Okay, so yeah, so let's see how will this happen. So you are, let's say you are given this array where you have this distances 3, 8, 10, 12, 17, 23, 25 and so on. So let me not write everything, but sorry, 30, 38. Okay, then what you'll do is you're just going to look till um, look till 10, because initially you're looking from 1 to 10. So you're going to increment your counter at 10. Then you will look from 10 to I mean just scan through the numbers, check the next entry, keep checking until you find a number which is larger than 20. So at this point you know that this is the previous one was the last petrol pump, so you should end up taking this. Then from this number you're going to keep scanning until you get a number which is more than 17 plus 10, which is 27. So that means the previous one you should for the previous one you should increment the counter and look for 10, I mean the next entry in the array which is larger than 10 plus that value. So this is just the linear scan of the array, right? You are not doing anything much, you're just scanning through the array. So this will take order and time. This is something you can show. So the other thing that we said is, okay, we have an algorithm where the approach is greedy in the sense that you're going as far as possible when you know that if you don't fill now you won't be able to move ahead, you're going to fill it. So it's greedy in that sense, and it runs in polynomial time. That's what we did, but I want to show the correctness. So you have to be convinced for your, okay, so just to make it clear, whenever you write an algorithm there's a correctness associated with it, which I am not saying will be asked in the exam, but you should be convinced it's correct, otherwise you'll end up writing an algorithm which is not correct. So this is the only reason I'm asking. So I'm not asking you to prove it, but just an argument of why this algorithm will always give you correct answer is what you need to be convinced about. So, any ideas why should it always give you the minimum number of um, petrol pump visits? Okay, so it's okay if you want to think about it, that's also okay. I'll not I'll not get into it right now, but this is something to think about, because otherwise you can end up with algorithms which are not correct. So that's it. That's all I wanted to say. But um, yeah, so I hope at least the algorithm is clear, and the approach, what is the greedy approach, is clear. If not, then please ask me right now. Okay, so then we'll do one more example of greedy. Mm, okay, so let's say that the question is that you have yeah, so let's say that you have some files. Okay, so you have different files. So this is of size maybe 2 MB. The other file f2, this is f1, f2 is of size 10 MB, and so on. So you have some files here. So let's say this is 32 MB f3, and finally you have fn, which is, let's say, um, 25 MB, and so on. So these are just any numbers. So basically you have some many files. They all have some size associated with them, and what I want to do is I want to perform merging. So I want to merge all of them all together to a single file. Okay, but the problem is I can't take all the n files, merge them all together, because I have limited resources. So what I can do is I can only merge two files at a time. So the input to you is an array where you have sizes of files. So this is, say, size of the first file was 2, 10, and so on. This is the input to you, and yeah, and what you want to do is you want to merge them. So the problem is that you can only merge two files at a time. Okay, so this is the problem. So you'll have to take two, merge them together, and keep on doing this. Okay, so one question that is there is how many times you will have to perform the merging operation. That is one question that um, you can try to answer. So I'll not get into it right now, but this is something that you should try out. So question is, how many merge operations are needed to get a single file. Okay, so this is one thing, but right now we'll not get into that. So um yeah, so right now the problem that I have is, so this is completely a different problem. The problem I have is that, let's say I perform a merge of file of size 2 and merge of files with size 10. Then the total cost I'm paying, so I'm paying some cost for merging, and the cost of merging is the size of A and B files, is the file size of A plus the file size of B. Okay, so for example, if I perform the merging of 32 with 10, then I'm paying the cost of 42, and then I have to combine, let's say, 2 and 25. So then I'm combining the current file of 42 I have with 25. Then the total cost I'm paying at this point is 67. Then I have this file of size 2 which is not yet merged. Then I'm, let's say, merging it with this. Then I'm paying the cost of 69. Whereas if I do this in a different order, let's say I first merge 2 and 10, I get a size of 12. Then I merge, say, 12 and 25. Then I get a cost of this is what, 37. And finally if I merge 32 with 37, Okay, in this case I'm okay, this is not maybe a good example, so I'll do 12 and 32 first. This gives 44. 44 and sorry, really sorry. So 12 and 25, this will give me 37. 37 and 32. Sorry, this is a really bad example that I came up with, but okay. But what I'm trying to say is that if you do it in different orders, you will end up spending different amount of different costs. So the question is, how should we merge it so that the total cost that we're paying for merging the all the n files is minimized. Shesha Sai has sorry if I mispronounce your name. So yeah, that answer is actually correct. So you're saying that we'll do a greedy approach. The greedy approach is that you're always going to find the minimum sized files and you're going to merge them. So the algorithm is that uh, you're going to pick the two files of minimum size and we're going to merge them. So let's say these are AB, then we're going to perform merge operation AB, and then notice that now you have n minus 1 file. So if there were n files here and you merge them, then these two files have now become a single file and the remaining n minus 2 files are as it is. So now you have n minus 1 files and the cost of this is updated. The cost of this file is the sum of the file sizes of A and B. So within this n minus 1 files, you are going to find the next two minimum and merge them and keep on doing this. So this is the greedy algorithm, and the claim is that if you do this, you will end up minimizing the cost. So the question is, what is the running time of this algorithm? So correctness we will not get into because it's something you can try out for yourself. I don't think you'll be expected to do this in the exam, so I'll not get into it right now. But the interesting question right now is, what is the running time? You can so for now you can assume that it's given in an array. If it's given in an array, then how do you find the minimum elements? So one thing you can do is you can always keep sorting. So let's say you sort all the elements. So first approach would be that you sort all the elements, then take the first two and merge them, add their entries, and then now the current entry that you have can actually, so let's say you had 2 10 then you have, let's say, 8, sorry, you have 11, then 14, 20, 24, let's say, and you merged the first two minimum, then the value of this new file is now 12, but 12 is not in its correct position. So you need to sort it again, because this could be anywhere. This could potentially be anywhere in the new array. So because it's the sum of the two entries, so in this case it so happens that it falls here, so you need to sort it again. That's a worst, like a very loose thing you can do. So it takes like n log n time to sort every time. You're doing this n many times. So so if you do this, you'll get n square log n. But can you do better? Do you really need to sort it to find the minimum element? So what you can do is, since you only need the two minimum elements, instead of sorting, what we will do is you will just scan through the array. In one scan you can find the two minimum elements. So this is something you can try out. Of course, in one scan you can find one minimum element. In the next scan you can find the second minimum element. But in fact, you can simply do it in one scan. So this is something you can try, but will not get into the details of it. So do one scan and find the first minimum and the second minimum. Okay, how much time will this take? This takes order and time. Now we have one new entry that is there with us. So this is, let's say, the new entry, and it's not like we said here, it's not that the correct position for this is here, it could be anywhere here. So what you do is, instead of sorting it again, we use the idea of insertion sort, where you have an array which is a part of array which is already sorted. You want to insert a new element in the sorted array. So what you do is you scan through these from left to right, find the correct position where it should be, and add it, and then push the remaining values. So this is something, the idea that you insert the min star in its correct position. So how much time does this take? This takes order n. This is the same idea that you saw for insertion algorithm. And now you have your array sorted, and you're going to repeat. You are again going to repeat that, find take the two minimums, and keep on doing this if you are sorting in the first place. So yeah, so if you do that, instead of being n square log n, it will actually take you n log n time to sort for the first time, and inserting is only n per entry. So this will take like order n square. So instead of n square log n, you are actually doing n square, which is slightly better than earlier. So with arrays you can say get up to quadratic. But if I want to actually truly get it to n log n, do you see how we can do this? If I want to get from n square to order n log n. Do you remember any data structure that you might have seen in the course that would help you bring the running time down? Good. Yeah. So what you do is you use min heap. So what is a min heap? It's a complete binary search tree where you have that the value at the root is lesser than the values of its children. This is the property that it satisfies. Therefore, if you want to find the minimum, it will always be in the root, and we can perform deletion operations, delete an element in the heap. This can be done in order n log n time. This is something we saw. You can delete some element in the heap. Then finding the minimum can be done in order one time. This is because you know that the root is at the minimum. But if you want to restore the heap, so if you simply delete it, this will disintegrate into two different trees, which is not what we want. We want to restore the heap. So if you think of finding the minimum or deleting with restoration, then this is going to take order log n time. Similarly, insertion can be done in order log n time. There are several other operations that you have seen, but for now we only need delete and insert. So what you will do is, if you want to find the first minimum is at the root. We will delete it and heapify the whole tree. So then you get another tree, and the next minimum is going to be the root of this tree. So then you have, now that you have the first minimum and the second minimum, we're going to add them together. So when you add them together, you get a new node with some value, and that needs to be inserted into the heap. So this insert process can be again done in order login time. So essentially you are performing two delete operations and one insert operation. So two delete are being performed to find the two minimums, and one insert is being performed to add the newly merged file. And this we are going to do n times, because eventually you need to do n mergings to get one single file. So this is 3 operations per merge, so 3 into n. And delete and insert operation, both of them take order login time. This is something you know from the heap data structure that you saw. Yeah, so this is 3n log n, or let's say order n login time. So if you do with arrays, you can get up to quadratic. Not saying that you can't do better, but the algorithms we saw, they do up to quadratic. But if you do heap, you can actually do in n log n time, which is asymptotically better than n square. So this is one example where you are actually using greedy approach to solve it, but if you make a good choice of data structure, you can actually improve the running time even further. Okay, so okay, so we have like 45 more minutes. Yeah, what we'll do is we'll quickly maybe, yeah, so MST is an important topic in the course, so I want to cover one example of it. So we'll just quickly recall the algorithm and run it on the example. We will not do the data structure part today because we don't have much time. So but we'll just recall what the algorithms do. So just give me a minute, okay. Okay, sorry. Okay, so you've been given this graph where the weight on the edge represents, okay, basically it's a weighted graph that is given to you, and you want to find the minimum spanning tree. So just to recall, what is a minimum spanning tree? It's a tree where which contains all the vertices in the graph, and if you sum up the costs, there are many trees that you can find, right? So in this case, for example, this is one tree, A, B, C, D, F, E, and it's a spanning tree because it covers all the vertices in the graph. And what is the cost of the tree? The cost of the tree is simply the sum of the edge weights that that are there. So in this case, it's 10 plus 15 plus 5, which is 30. So the cost of this tree is 30, and there are many other trees that you can find. So for example, this is another tree, and you sum up the edge widths and you'll find the cost of it. So what we want to do is want to find one whose weight is minimum. That's the MST problem that we said. So we saw two algorithms, at least two algorithms for solving this. One was the Prim's algorithm, the other was the Kruskal's algorithm. Both of them run in polynomial time, and we saw how you can make a good choice of data structure to bring down the time complexity. So let's see how the algorithm, run the algorithm on this example. So what does Prim's algorithm do? It just it just takes the minimum weight edge, which is in this case 1. So what we'll do is we'll take this 1 and include it in our tree. Then we're going to take the next minimum edge. So what is that? That is CE. So we're going to take this. The next minimum edge is of weight 3, but then there are 2 of them. So which one do we choose? If you choose BE, then you are actually forming a cycle. So you're not finding a minimum spanning tree, you're actually finding a cycle. So what you'll do is you'll discard that edge and take the next one. So what is the next minimum we have? It is 4, and 4 does not form a cycle with the current tree that we have. So you take 4. The next minimum is 5, but 5 we can't take because otherwise this will form a cycle. So this is something we don't want. The next minimum that you see then is 7. So 7 we can take, it does not form a cycle. Next minimum is 8. So 8 I cannot take because this will form a cycle. So then I have to take 9, and 9 I cannot take because that would form a cycle, and we already have a tree which covers all the vertices of the graph. So this is the minimum spanning tree given by this algorithm. And what is the cost of it? The cost of the MST in this algorithm is 2 plus 1 plus 3 plus 4 plus 7, which is 17. Okay, and the minimum spanning tree is unique if all the edge weights are distinct. So if you have distinct edge weights, then the MST is unique. Okay, but the other way around is not true. It's not necessary that if the edge weights are not distinct, then there will be multiple MSTs. That is not true, and the example is this itself, because here you have 2 edges with different weights, but there is only one minimum spanning tree in this graph. So you cannot find any. So if you take any other spanning tree in this graph, you will find that its weight is strictly larger than 17. So okay, so now we'll run our Kruskal's algorithm on yeah. Yeah, so just to mention, I'll not get into the data structure, but just want to recall that we had done a find union. We had used find union data structure to get better running time for this. So we'll just quickly run the algorithm on Kruskal's algorithm on this same example. Okay, so what does Kruskal's algorithm do? What it starts with a vertex, starts with any vertex, and it takes the least edge that goes through it. So let's say I am going to start at 1, and start at A. There are 2 edges that are outgoing from there. I'm going to take the one which is of minimum weight. So we're going to take 4. Okay, and now our structure looks like this. We only have AC. This is our connected component. Now we are going to look at all the edges that go outside A and C, and we are going to find the one with minimum weight, so which is in this case 1. So I'm going to take 1, and now our structure looks like this. It's ABC, and we're going to look at all the edges that go outside and find the minimum of this. So out of 5, 3 and 2, the minimum is 2, so we're going to take 2. Now our structure looks like this, and what are the outgoing edges? Edges outgoing are 5, 3, 3, and again minimum is 3, but we can't take this one. Sorry, this is not even in the so this is not even in our outgoing edge, because it's an edge contained within which would create a cycle. So the minimum that you have is 3 here again. You end up taking that. Now our structure looks like this with A, C, B, E, and D, and the outgoing edges from the structure are DF and EF only. So the minimum one is 7. So you'll end up taking this, and again you got the same tree. So in this case, because there is a unique MST, both the algorithms give you the same MST as an output. But if there are multiple answers that are possible, then different runs of algorithms may give you different MSTs, but all of them are valid. So there was also this data structure choice that we made for Pascal's algorithm to get better running time, but again, which was a priority queue, and we did a heap based implementation of this. This is the context in which we saw the priority queue. We saw the heap sort, but we'll not again get into it for the yeah. So maybe I'll skip this question also. This is the Huffman encoding part, but I think we've done enough questions on it earlier, and last time we did not get to do this Ford Fulkerson. So I want to do it for now. So hopefully we'll have more time to do other questions, but let's see. So okay. So maybe I'll just quickly recall what the problem is, what the flow is. Okay, so the problem is that you have this you have a graph, a directed graph that is given to you, and there is some target node. So, and there are some weights that are associated with them. So maybe I'm just writing random numbers. So basically you have a source node S, you have a target node T, and this is a weighted directed graph. And what I want to do is I want to pass as much flow as possible. So what this 2 says is that the capacity of this edge is 2. That means I can direct a flow of at most 2 weight 2 through this edge. From this edge I can pass a flow of size of at most 7. I can't pass 8, a flow of 8 through this, and so on. That is what it denotes. Okay, and so these are the capacity constraints. So there are two types of constraints. One is the capacity constraint, which means that the amount of flow that we are passing through an edge E, this is the flow that is passed through edge E, is at most the capacity of E, which is the weight that is written on it. Okay, and we'll assume that all the weights are positive. Let's not go into the case where it's negative and so on, which you can handle in some cases. So for now, let's assume that these are positive. Okay, so this is the first constraint. That means if the capacity of this particular edge is C, I cannot pass a flow more than C. The second constraint that you have is what is called the conservation constraint, which means that if there is a flow through this node outgoing flow through this node, we are passing a flow of maybe if the incoming flow on this node is of say 2, then the outgoing has to be 2. You cannot pass a flow of more than of less than 2 or more than 2 through it. If the total incoming flow is x, you have to push it back. It cannot preserve it cannot contain some flow with itself. So what that means is total inflow on any vertex is equal to total outgoing flow. So for now, let's say it has only yeah, at this moment it can this node B can only take a 2, but let's say I pass something more. Let's say I pass 3 through this, 3 through this, and yeah, and 1 through this. So what is the total flow that is incoming? 1 through this node and 3 through this path. So totally there is a flow of 1 plus 3, which is 4. But this we cannot do because it can only the outgoing flow is bounded by 3. I cannot pass a flow of more than 3 through this. So that is what this conservation constraint is. So first is I can't pass a flow more than the capacity. Second is total flow that is coming in should be equal to the total flow that is going out. So these are the two constraints, and given that I want to pass as much as flow as possible from S to T. That is the question. So again, you can notice there is some kind of a maximization flavor to it. So yeah, so it's an optimization problem. So the question that we are asking is, given these constraints, find the maximum flow from S to T. Okay, so so there are several algorithms for this, but the one that we are going to discuss, which is the Ford-Fulkerson algorithm. So what does the Ford-Fulkerson algorithm say? Okay, so if you know the algorithm, can you maybe try this out? I'll just take a small I'll just come back in 5 minutes. Okay, sorry about the sorry about the delay, but please take this time to solve it out, or if you have any questions, think about it. I'll be back in a minute. Okay, hi. Sorry. So, yeah. So if I'll just yeah, if you have solved it already, then can you tell me the maximum flow that you were able to push through this network? Okay. So what we'll do is 4. Okay. So how did you pass 4? So what are the paths that you chose? So 7, 4, 5. So from this you could pass 4. Okay. But then you can also additionally, okay. Sorry. Just let me charge the pencil once. So from um yeah, so from here you were able to pass 7, 4, 5. I mean, this is the so the maximum you can push through this is 4, because 4 is the bottleneck. Even if you pass 7 through this, you won't be able to push it out. That's why you need to push 4 through all of them, so that finally T gets 4. But then you can also push 2 through this S to B, push 2 through this, and 2 through this, so that it looks like this. So I'll just erase this. So you can push 2 through this. The red one indicates the flow that I'm passing forward. So 2 through this again, because this is incoming, so 2 should also go. And similarly, if 2 is incoming here for this node, then 2 should also go out. So I'm passing it like this. Then I'm passing 4, 4, 4. So this is 4, 4, 4. So what is the total flow that reaches um yeah, reaches this right now it's 6. I claim that you can actually do even more. You can actually make it 7. So how can we do that? Can you see one more path here? One more path through which maybe I can push a flow of 1. I'll just write label to the node so that you can tell me the name of the path. So this is A, B, C, D. So okay, I'll just write it this way. This is not 3 of 3. Right now I'm using 0 of 3, 0 of 6, because I'm not passing anything to this and this right now. Can you identify one more path? S, A, B, C. Good, exactly. So you're saying that, look here, there is a total capacity of 7. I'm only passing 4. Maybe I'll pass one more through this. So I'll pass 3, I'll pass 5, out of which 4 is yeah, out of this 4, out of this 5, 4 is already going from A to D, so I'll pass a flow of 1 through this. So we'll pass 1 through this. Now the total incoming here is 2 plus 1, 3. So total outgoing should also be 3 by the conservation property. So 3 is outgoing. Similarly, for the C, the total incoming flow is 3. So we'll pass 3 outside through it. So you're going to get a total flow of 3 plus 4, which is 7. And yeah, you can't do better than this, because there is a bottleneck of 3 which is totally used here. There's a bottleneck of 4 which is totally used here, and you cannot find any other path from S to T where there is some edge whose capacity is not fully exhausted. Any path will give you some edge which is fully exhausted, so that the maximum flow that you could pass here is 7. Okay, so if so using the same idea, so what we're doing is we're finding a path where we can push flow. If it's possible to push, we're keeping on pushing. Find a path and keep on pushing. So this is the idea that we have. So using that idea, can you I've not defined what the Ford-Fulkerson algorithm is as of now, but using the same idea, can you just take a couple of minutes